The National Electrical Code does not explicitly state the maximum distance between the elevator controller, typically located in the machine room, and the elevator motor. However, several factors must be considered to ensure the safe and reliable operation of the elevator system. Firstly, consider the wire length. The length of the wires connecting the controller to the motor should be minimized to reduce voltage drop and minimize power loss. National Electrical Code Article 620 requires that the length of motor circuit conductors should not exceed 25 feet, which is 7.62 meters, unless otherwise allowed by an approved method. Secondly, consider the signal strength. The controller communicates with the motor through electrical signals. The distance between the controller and motor should not be so great that the signal strength is compromised. For modern elevator systems, wireless communication may be used, eliminating the need for physical wiring connections. Thirdly, accessibility is crucial. The machine room should be easily accessible for maintenance and troubleshooting. The distance between the controller and motor should allow for convenient access to both components. In general, the controller and motor are located within the same machine room. The distance between them typically ranges from a few feet to several feet depending on the size and layout of the machine room. However, there are exceptions. In certain cases, it may be necessary to locate the controller and motor at a greater distance from each other. For example, the controller may be located in a remote location to reduce noise and vibrations in the elevator shaft. Another exception is when the motor may be located at the top of the houseway to reduce the weight and inertia of the moving parts. If a greater distance is required, special considerations should be made, such as using larger wire sizes, shielded cables, and signal boosters. Approval from the elevator inspector and the local building code authority may also be required. Therefore, while the National Electrical Code does not specify maximum distance between the elevator controller and motor, it is important to consider the factors discussed above to ensure a reliable and safe operation of the elevator system. In most cases, the controller and motor will be located within the same machine room with a distance of a few feet to several feet. To further elaborate on wire length and voltage drop, it is important to understand the relationship between conductor length, conductor size, current, and voltage drop. Longer conductors will naturally exhibit a greater voltage drop for a given current. This is because the resistance of the conductor increases proportionally with its length. The National Electrical Code provides guidance on calculating voltage drop in branch circuits and feeders. It's recommended to limit voltage drop to no more than 3% in branch circuits and no more than 5% in feeders. Excessive voltage drop can lead to various problems, including reduced motor performance, overheating of conductors, and malfunctioning of sensitive electronic equipment. To mitigate voltage drop, larger conductor sizes can be used. Larger conductors have a lower resistance per unit length, which reduces the voltage drop for a given current. The appropriate conductor size can be determined using voltage drop calculations outlined in the National Electrical Code or by consulting with a qualified electrical engineer. When considering signal strength, particularly in systems that rely on wired communication between the controller and the motor, the type and quality of the cable used are important. Shielded cables can help to reduce electromagnetic interference, which can degrade the signal and cause communication errors. A cable should also be properly terminated and grounded to minimize noise and ensure signal integrity. In cases where wireless communication is used, the range and reliability of the wireless link should be carefully evaluated. Factors such as antenna placement, signal obstructions, and interference from other wireless devices can affect the performance of the wireless communication system. Signal boosters may be necessary to extend the range of the wireless link or to overcome signal obstructions. Regarding accessibility, the layout of the machine room and the placement of the controller and motor should allow for easy access for maintenance personnel to inspect, troubleshoot, and repair the equipment. Sufficient clearance should be provided around the equipment to allow for safe and efficient working conditions. The machine room should also be adequately lit and ventilated to ensure a comfortable and safe working environment. In situations where the controller is located remotely from the motor, additional considerations should be taken into account. The remote location should be environmentally controlled to protect the controller from temperature extremes, humidity, and dust. The remote location should also be secure to prevent unauthorized access to the controller. The use of a remote monitoring system can provide valuable information about the status of the elevator system and can help to identify potential problems before they escalate. This system can monitor parameters such as motor current, voltage, speed, and position, and can alert maintenance personnel to any abnormal conditions. When locating the motor at the top of the hoistway, it is important to ensure that the hoistway is adequately ventilated to prevent overheating of the motor. The hoistway should also be designed to withstand the weight and forces generated by the motor and the elevator car. The use of a counterweight system can help to reduce the load on the motor and the hoistway structure. In addition to the National Electrical Code, other codes and standards may also apply to the installation of elevator equipment. These may include local building codes, elevator safety codes, and Americans with Disabilities Act accessibility guidelines. It is important to consult with the local building code authority and the elevator inspector to ensure that the installation meets all applicable requirements. The selection of appropriate wire sizes for elevator motor circuits is governed by National Electrical Code Article 430, which covers motors, motor circuits, and controllers. This article provides detailed requirements for conductor ampacity, overload protection, and short circuit and ground fault protection. The ampacity of the conductors must be sufficient to carry the motor's full load current, as determined from the motor nameplate. The National Electrical Code provides tables that list the ampacities of various conductor sizes based on their insulation type and temperature rating. Overload protection is intended to protect the motor and the branch circuit conductors from excessive heating due to motor overloads. Overload protection can be provided by thermal overload relays, fuses, or circuit breakers. The overload protection device must be sized appropriately for the motor's full load current. Short circuit and ground fault protection is intended to protect the motor, the branch circuit conductors, and the equipment from damage due to short circuits or ground faults. Short circuit and ground fault protection can be provided by fuses or circuit breakers. The short circuit and ground fault protection device must be sized to protect the circuit against high-level fault currents. When installing elevator wiring, it is important to follow the National Electrical Code requirements for wiring methods. The National Electrical Code specifies the types of wiring methods that are permitted for use in various locations and applications. For example, rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit are commonly used for elevator wiring. The wiring method must be properly installed and supported to ensure its mechanical integrity and to prevent damage to the conductors. All electrical connections must be made in accordance with the National Electrical Code requirements. Connections must be tight and secure to prevent loose connections, which can cause overheating and electrical hazards. Wire connectors must be listed for the intended use and must be properly sized for the conductors being connected. Grounding is an essential safety measure that helps to protect people and equipment from electrical shock hazards. The National Electrical Code requires that all electrical equipment be properly grounded. The grounding system must provide a low impedance path for fault currents to return to the source, which will cause the overcurrent protection device to trip and energize the circuit. The grounding conductor must be properly sized and installed in accordance with the National Electrical Code requirements. In addition to the general wiring requirements, there are also specific requirements for elevator wiring. National Electrical Code Article 620 covers the electrical equipment and wiring used in elevators, dumbwaiters, escalators, moving walks, platform lifts, and stairway chairlifts. This article provides requirements for disconnecting means, overcurrent protection, control circuits, and other aspects of elevator wiring. The disconnecting means must be readily accessible and must be capable of disconnecting all ungrounded conductors of the elevator circuit. The overcurrent protection device must be sized to protect the elevator motor and the branch circuit conductors. Control circuits must be designed to prevent unintentional starting of the elevator motor. When working on elevator electrical systems, it is important to follow safe work practices. Always to energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow lockout/tagout procedures to prevent accidental re-energization of the circuit. Be aware of the potential hazards associated with elevator electrical systems such as high voltage, moving parts, and confined spaces. Only qualified and trained personnel should work on elevator electrical systems. In summary, while the National Electrical Code does not specify a maximum distance between the elevator controller and motor, several factors must be considered to ensure the safe and reliable operation of the elevator system. These factors include wire length, voltage drop, signal strength, accessibility, and applicable codes and standards. By carefully considering these factors and following safe work practices, you can ensure that the elevator electrical system is installed and maintained in a safe and reliable manner. Additionally, regular inspections and maintenance of the elevator electrical system are essential to identify and correct any potential problems before they lead to equipment failure or safety hazards. These inspections should be performed by qualified elevator technicians who are familiar with the National Electrical Code and other applicable codes and standards. During inspections, technicians should check for loose connections, damaged wiring, worn components, and other signs of wear and tear. They should also verify that all safety devices are functioning properly. Any problems that are identified should be promptly corrected to prevent further damage or safety hazards. Regular maintenance tasks such as lubricating moving parts, tightening connections, and cleaning equipment can help to extend the life of the elevator electrical system and to prevent breakdowns. A well-maintained elevator electrical system will provide reliable and safe transportation for building occupants. In conclusion, the distance between the elevator controller and the motor is not explicitly defined by a specific maximum length in the National Electrical Code. However, adherence to good engineering practices, consideration of voltage drop, signal integrity, accessibility, and compliance with all relevant codes and standards are crucial for a safe and reliable elevator installation. Always consult with qualified professionals and local authorities to ensure that the installation meets all applicable requirements and provides a safe and efficient transportation system.